So welcome to the October session of Everything I Forgot from Stats class. Today we're going to talk about logistic regression. I know Tyler covered a little bit in his talk last month on nonlinear, and Deb's going to touch base on multiple regression next month. So we've got a nice little group of regression sessions going on. So today we're going to take just a slightly deeper dive into logistic regression. Now, just a caveat, we're not going too deep because I didn't write a book, but if you're interested in a book, there are plenty of them out there. So I'm sure the same is true for any type of statistical test that you are interested in taking a deeper dive on. So through this in here, I think most of us know, but statistical tests follow a flow chart. So they're like building blocks on each other. And today we're going to be looking at logistic regression. So our outcome variables categorical, and we have greater than 2 groups and continuous. Exposure variables are greater than 2 groups and continuous. So what is logistic regression? It is a type of generalized linear regression. It's also known as the logit model. And so we're going to use logistic regression for classification and predictive analytics when we are estimating the probability of an event occurring on a given database, set of databases for independent variables, but when our dependent variables or our predictors are binary. So the dependent variable is bound between 0 and 1. So we're looking at the outcome of the probability. And the logit transformation is going to be applied to the odds. So we're going to look at the probability of success divided by the probability of failure. Can't really talk about logistic regression without comparing it to linear regression because they are so similar and they're in the same family. So just a quick review of linear regression. Linear regression is used to predict or forecast values. Logistic regression is used for classification. So when we look at linear regression, it's used when you're looking at a relationship between a continuous dependent variable and one or more independent variables. And then you just plot that line of best fit through the data points. So you're going to get your regression line that you see in the graph below. So when we're looking at linear regression output, we can estimate the value of the dependent variable on the independent. And we can say that the value is within some kind of, we can say that a value is going to fall within some kind of predicted range. When we look at logistic regression, this is used to estimate the relationship between a categorical dependent variable and one or more continuous independent variables. So it's going to produce a probability, but the function is going to transform. So unlike your linear regression, where you have this line of best fit, logistic regression is going to essentially take the ends that fall above or below 0 and transform them into an S-curve. And that S-curve or your sigmoid function is going to convert any value from negative infinity to infinity to either 0 or 1. So we get this nice little curve. Both models are used in regression analysis to make predictions about future outcomes. So linear regression is going to be typically easier to understand because anytime we use functions to transform data, it just makes it a little more complicated and a little more difficult to understand. Linear regression also doesn't require as large of a sample size as logistic regression does. Without the larger sample for logistic regression, you may not have sufficient statistical power to detect any kind of significant effect. So I found this little table just that comparing the differences between linear and logistic regression. So linear regression, your target is an interval variable. Logistic, your target is a discrete binary or ordinal variable. With linear regression, you're looking for predicted values that the predicted values are the mean of the target variable at the given value of the input variable or the independent variable. With logistic regression, the predicted values are the probability of the particular levels of the given variables of the independent variable. So in linear regression, we're solving for regression problems. In logistic regression, we're solving classification problems. So when you look at linear regression, an example is, what is the temperature? How can we predict the temperature? In logistic regression, we can say, will it rain or not? What is the probability that it's going to rain? And then as you saw, the output for the linear regression, you're going to have a straight line, and logistic regression is an S-curve. Well, the problem is you can't really solve on an S-curve. So we do have to transform that a bit into something that we can make more understandable. So we're going to do that here in just a second. These are a couple of the questions, types of questions that we can answer. How does the probability of getting lung cancer change for every additional pound a person is overweight and for every pack of cigarettes smoked per day? Do body weight, caloric intake, fat intake, and age have an influence on the probability of having a heart attack? So we're looking for yes, no outcomes. There are three types of logistic regression. So you have binary logistic regression, where that dependent response variable is dichotomous in nature. This is the most commonly used approach, and it's one of the most common classifiers for binary classification. So if you have a binary dependent variable, more oftentimes than not, you're going to be using a binary logistic regression. Multinomial is when you have three or more possible outcomes. However, there is no specified order. And then ordinal logistic regression is when you have dependent variable that has three or more possible outcomes with a defined order. So what are our assumptions for logistic regression? So first, the dependent variable is dichotomous in nature. Secondly, there are no outliers in the data. And you can do that by converting the continuous predictors to standardized scores, and then remove anything that is less than 3.29 or greater than 3.29. And then the third major assumption is that there's no multicollinearity among the predictors. And so multicollinearity is, of course, when you have extremely high correlation between your predictors. And so to evaluate that, you can use a correlation matrix, and anything that is greater than 0.90 is suggested to be to have multicollinearity. And so as long as your correlation value is below 0.9, then your assumption is presumed to have been met. All right, so this is our simple logistic regression equation. And here, the predicted probability that your dependent variable for a given case, right? So that's the probability that Y is true for your case. So you have 1 over 1 plus the mathematical constant or the base of the natural logarithm, sorry. So that's going to be roughly 2.72. Then you have your intercept, which is the constant estimate from the data. You have your coefficient for the input, and then you have your observed score for your case. And so essentially the very essence is just estimating your intercept and your B coefficient. All right, so let's look at a case. We're going to perform a logistic regression in SPSS. I borrowed this case from Statology, and their example is whether or not college basketball players get drafted into the NBA based on their average points per game and their division level. So when we're first going to run it, in case you don't know, logistic regression is found under regression and then binary logistic regression in SPSS. In the window that pops up, we're going to drag our binary response variable into the box labeled dependent and the two predictor points, variables of points and division into the box labeled block 1 of 1. You're going to leave method set to enter and then click OK. And I have this. Oh, look, there it is too. So here we go. We just drag and drop. We leave methods set to enter and we click OK. So it's going to give us output. This is the first two of the three tables it's going to give us. It's going to give us a model summary. So our R square is going to tell us the percentage of the variance in the response variable that can be explained by the predictor variables. In this particular case, it's 72.5% of the variability in the draft. We are also going to have a classification table. So this classification table gives us the overall percentage of observations that the model was able to classify correctly. And in this case, you can see that the model was able to correctly predict the draft results for 85.7% of the players. And then the third table it's going to give us are the variables in the equation. So it's going to give us the WALD, which is used to determine whether or not each predictor variable is significant. It's going to give us the p-value that corresponds to the WALD test. And then we're going to get the exponentiation of the B coefficient. This is your odds ratio for your predictive variable. So if you look here, the change in odds of a player getting drafted associated with a 1 unit increase in a given predictor variable. So for our example, the odds of a player in Division 2 getting drafted are just 0.339 of the odds of a player in Division 1 getting drafted. Similarly, each additional unit increases in points per game is associated with an increase of 1.319 in the odds of a player getting drafted. So this is a really, really simple example, but I think it gets the point across. So we can then use the coefficients, which the coefficients are going to be our values in the column labeled B, to predict the probability that a given player is going to be drafted using the probability formula. And so when we plug in the numbers over here, so we're pulling our numbers from our table, we see that the resultant probability is 0.787. So if you kind of to follow this, so this is our beta, negative 3.152, so our constant. 0.277 is the constant for points. 1.82 is the constant for division. So we're going to take this and then we're going to divide it by, essentially you're pulling those same variables over the constant values. In addition, on the previous slide you saw, we're looking at 20 players and we're looking at a degrees of freedom of 1. So since the probability is greater than 0.5, so we're at 0.787, we would predict this player would get drafted. If you have these results, how do you report them? So you can use terminology similar to the following. Logistic regression was performed to determine how points per game and division level affect basketball players' probability of getting drafted. A total of 14 players were used in the analysis. The model explained 72.5% of the variance in draft results and correctly classified 85.7% of cases. Another way to interpret the logistic regression is actually to report the odds or the odds ratios. So exponentiating the beta estimates is a common way to transform those into odds ratio, which are much more palatable and understandable. So odds ratio represents the odds that the outcome is going to occur in a particular event. And if an odds ratio is greater than 1, then the higher it is, the higher the odds of the outcome. If it's less than 1, the lower the odds. In our example, we could say something like estimating the odds of a player being drafted to the NBA, given that the individual played Division II and the odds ratio for division was 0.339, we'd interpret the odds ratio as the odds of being drafted of Division II players decreased by a factor of 0.339 when compared to Division I players, holding all other variables constant. Similarly, you could say the odds of a player in Division II getting drafted were just 0.339 of the odds of a player in Division I getting drafted. Additionally, when you look at unit increase in points, each additional unit increase in points per game was associated with an increase of 1.319 in the odds of a player getting drafted. Okay, so that is a very brief way to interpret a logistic regression. A couple of things to be mindful of with logistic regression is overfitting. And so overfitting is an important consideration, because if you fully and completely define a model, you may explain a whole lot of the variance. Like the more variables you put into the model, the more closely you may explain the variance. But the problem is, if you add a considerable number of variables that aren't generalizable, then you can result in a model that is overfit, which is going to reduce the generalizability beyond the data on which the model is fit. So if I have 15 different independent variables, the likelihood that anyone else is going to be able to fit that model to their population is pretty slim. There's kind of a balance there between not having enough and adding too many in order to explain the variance. All right, there's one other caveat that I want to mention, and that's reporting the R-squared. So there are numerous pseudo R-squared values that have been developed for binary logistic regression, and they should be interpreted with caution. So as I said earlier, anytime you are utilizing transformations, things just get a little trickier. And when I was actually taking my multiple regression course, the professor explained it in terms of Oz. So we talked about Dorothy in Kansas and Dorothy in Oz. And so that's how I've always referenced transformations and regression as this Oz, where it's not a one-to-one. You have to bring it back into reality or the black and white for people that don't understand how those transformations work. And so you do have to interpret these pseudo R-squares with caution, because they live in Oz. So in that transformation, they may have computational issues which cause them to be artificially high or artificially low. So whenever you look at a pseudo R-square, you just want to make sure that it makes sense when you look at the data as a whole and when you look at your outcomes as a whole. One suggestion of a better approach, perhaps, is to present any of the goodness of fit tests that are available. And so when you run your tests, you're going to have goodness of fit, and it's generally a good practice to just report that when you're reporting out your results. All right, so let's talk about a couple of advantages and disadvantages when it comes to logistic regression. So logistic regression is easier to implement, interpret, and very efficient to train. But if the number of observations is less than the number of features, then it should not be used because it may lead to overfitting. It makes no assumptions about distributions of classes in feature space. It does construct linear boundaries. It can easily extend to multiple classes by using multinomial regression and a natural probabilistic view of class prediction. A disadvantage is that in linear regression, independent and dependent variables are related linearly, but logistic regression needs that the independent variables are linearly related to the log odds. So again, we're transforming those data. An advantage is it not only provides a measure of how appropriate a predictor is, but also its direction of the association. A disadvantage is that it can only be used to predict discrete functions. So the dependent variable is bound to a discrete number set. An advantage, it's very fast at classifying unknown records. A disadvantage, nonlinear problems can't be solved with logistic regression because it has a linear decision surface. An advantage, good accuracy for many simple data sets, and it performs well when the data set is linearly separable. A disadvantage, logistic regression requires average or no multicollinearity between independent variables. Another advantage, it can interpret model coefficients as indicators of feature importance. Disadvantage, it's tough to obtain complex relationships using logistic regression. And then I think these are the last advantage is that logistic regression is less inclined to overfitting, but it can overfit in high dimensional data sets. A disadvantage, in linear regression, independent and dependent variables are related linearly. Oh, that's the same one that I had earlier. Sorry about that. Not sure what happened there. We'll assume there's another disadvantage there. I wanted to throw a couple of resources in. Not sure if you guys use these, but StatsQuest is he has a YouTube channel, and he has a lot of videos on various stats tests, and some of them he takes a pretty deep dive into. Usually there's a pretty good one on actually series on logistic regression. And so if you don't watch his videos, are pretty good. He's a little bit quirky. His rhythm and cadence is interesting, but his information is strong. And then also Statology. So I actually got that example from Statology. That's a good reference too. All right, so that was all that I have prepared, and I kind of flew through that. Anybody have any thoughts, comments? Did I just get something completely wrong? Tyler, you can tell me if my formula was wrong. I don't calculate things by hand. Courtney used to do that, but I don't. I trust my computer programs.